Oh, is it time? The video's on? Hello? All right. Oh, hello, everyone. It's so good to see you, and you, and you, and you. All right. There's some things that have to be taken care of right now, as you can see. All right. Anybody else want to pour a drink? Is that... No? All right. Well, hopefully you can drink along from your seat. This is the Dan Kaminsky drinking game. And as you can see, there are some essential ingredients here. There's 2 parts water, 1 part Jack Daniels. And that is basically what makes up the man in front of us. And before I bring on the miracle of science, maybe turn off your, I don't know, your deck phones or do something. Press some buttons so that it's quieter. Because Dan, he loses focus and then he drinks even more. Without further ado, and not having explained anything about the man whose speech attracts people from around the world, he's just back from his mission in South Ossetia where he helped people. I need to slow down because you don't know where I'm going to end up.
Monkeys.
I was trying not to give further ado, but I gave further ado. So, onwards with Dan Kaminsky, ladies and gentlemen.
What's up, guys? First of all, I want to apologize to everyone for not actually having the talk description out. I figured that would eliminate any partial disclosure stuff and give me a nice drama-free summer. That didn't happen. So, those who don't know me, I am Dan. We're not actually at Black Hat, so we can ignore that. But I tend to play with toys. You know, my thing that I'm looking at this year is authentication. I think we can pretty much all agree. Auth sucks right now. ODay gets all the attention, but when you actually look at the data, about 60% of all vulnerabilities, of all actual penetrations, come in from authentication flaws, from passwords. There's no password, there's a bad password, it's a default password, it's a stolen password, it's my password. I mean, you know, passwords suck. They're awesome because they actually work. They suck because in large quantities, the human mind just cannot deal. There's a certain amount of entropy of randomness that is needed in passwords. You can do it good for one site, you can do it bad for many sites, but you can't do it good for many sites without writing things down, which is itself bad. So you're kind of backed into a corner. Now we can make passwords work barely. I mean, you can machine generate them, we can rapidly cycle them, we can use LeetSpeak as a security technology. Guys, I think the bad guys have figured out sometimes I is a 1. So what we keep trying to do is, why don't we eliminate passwords? You know, we could have like our computer device talk to its computer device, and if there's one thing we figured out how to do with computers, it's memory. So why don't we have computers remember stuff? And why don't we have like public-private key, you know, with smart cards? We'll use PKI, public key infrastructure with x509 technology. If only we cared enough, we could totally eliminate this problem. You know what? I found this image on the internet, which is wonderful. It explains exactly what is going on. And it's, if we just had a big enough Care Bear, we could totally ride this pony. No. Hell no. Guys, look, business has cared enough to invest hundreds of millions of dollars in x509-based technology over the last 10 years. It hasn't been working. Now, about 5 or 6 months ago, I started publicly talking about DNSSEC, saying, holy crap, this technology is not actually a complete cluster. The reason why is because I was in the middle of looking at a complete cluster, so I knew what they looked like. You have to understand, I've made a complete 180 on this DNSSEC thing. I spent almost a year being like, I do not want to hear crap about this stuff. And then I started looking at x509, and I'm like, this DNS stuff ain't bad. So that's kind of my theory here. I do think that we need to rethink the foundations of internet security if we're going to do something about the authentication problem. That doesn't mean we're going to build some second internet. You would not believe how many people out there are like, the solution to all our problems is, we'll make another one, and this one will be safe. I won't. Stop it. You're just asking for money, and like lots of it. I understand. I'm cool with that, but it's not actually going to work. So it's important to talk about why things aren't working. For those in the audience who aren't familiar with x509, I don't want to go into too much depth on it, but I want you to think about your passports. If you show up at a foreign country, they don't know who the hell you are. They don't know anything about you. But you know what? They look at their passport and they're like, all right, we've heard of Belgium. Belgium's okay. We'll believe who you are. Cool. And that's kind of ultimately what x509 is intended to allow you to build. It allows you to build a system where you can go to a website. You have no idea who the website is, but you know who VeriSign is. And VeriSign says, yeah, whoever this is actually Bank of America. Or this is actually whatever. This is actually the key associated with Bank of America. So, indeed, x509 has about one and only one real success story, and that would be SSL. This is something of a historical quirk or accident. Somehow, magically, in the mid to late 90s, the people got convinced if you wanted to give a credit card number over the internet, there had to be a lock, and for there to be a lock, there had to actually be strong cryptography. This is a miracle that they actually managed to pull off, attaching something worthwhile to money. Thank you, guys. That is actually pretty cool. This is ultimately the most popular crypto solution we have. We have about 1 million SSL endpoints on the internet today. There's about a couple 100 million IP endpoints on the internet. We're not doing that well. And of that million, about half aren't actually doing anything cryptographically interesting. So we're really not doing that well. So let me tell you how you actually get a certificate. And this is one of the funny things. Everyone always says, how could you be arguing for DNSSEC? How can we actually put our security trust into DNS? And then I'm like, why don't we look at SSL? The first step in getting a certificate for a website is you go ahead and you go to DNS and you register the name for a website. That's step one. SSL actually starts with DNS. The next thing you do is you develop generate a public and private key pair. This is the computer equivalent of a face and a photograph of the face. You provide the public key to a certificate authority. This would be VeriSign or Thought or one of these companies out there that the browsers trust. This key is provided along with the name that was extracted from DNS. That happens over what's called a certificate signing request. Now, the certificate authority doesn't know who you are, so what's it do? It goes to DNS. It says, hey DNS, what's the email address of this guy? It gets an email address out of what's called the Whois database. And then it goes, hey DNS, where the hell is its mail server? And then it sends a mail and says, can I actually provide this certificate? And if you mail back and say, yeah, it's fine, it will go ahead and issue a certificate, which is returned to the user. And now you have a certificate for www.whatever.com. Now, some of you in the audience, if you're an x509 guy, you might say, oh, you're totally oversimplifying. It doesn't work like that in my system. Screw you, the world doesn't use your system. This is how it really works. What I just described is called domain validation. Now look, there are totally better CAs out there. I bet there are better CAs run by people in this room. They do like DUNS lookups and phone calls. They like send a lawyer to get a blood sample. And that's all great and wonderful, except the browser does not give a shit. Because there are totally crappier CAs out there, and they're just as good for providing a lock. The first, and this is not elite, this is not cool, this is not crazy ass stuff, that's for later in this talk. This is why x509 isn't working that well. You cannot exclude crappy certificate authorities. If you have one certificate authority that is great, I mean a total boutique shop, and they'll give you a lock only if you do something hardcore. And then you have these other guys, the fact that the other guys are out there creates a race to the bottom. The bad guy doesn't attack the good people. The bad guy attacks the really lame people and ultimately gets a certificate just the same. This has created a race to the bottom. Now, DNS does not have this trait. DNS has 3 separate layers, all of which just are completely immune to this sort of attack. You start with the root. The DNS roots are an utter pain in the ass to deal with. This is great because it means the bad guys can't deal with them. There's this old quote in cryptography which says a certificate authority is only as good as the money they refuse to take. The root will not take your money. This is awesome and wonderful. The root is basically an adjunct of the very same state system that provides concepts such as Belgium and Austria and the Netherlands. So the root really does not care what money you throw at it. It's just not accepting your stuff. Next layer, you have the registries. You have VeriSign that owns COM. You have Affiliates that owns org. You have individual companies that, yes, they individually could be bribed, but yes, they have an area that they have exclusive control and exclusive accountability. There was a top-level domain that was filled with spyware to the brim. Every name that it would look up, if you saw a lookup to this TLD, you were pretty sure your network was infected. You know what happened? The registry behind it said, holy crap, we're starting to lose money. We're going to go clean up our mess. And right now, that TLD, because one company was behind it, it got cleaned up. Bad stuff got taken off the internet. Cool. Finally, we have the registrars. And I don't know if people understand how interesting this system is. It would be a pain in the ass if you had only one company, you had to go to them if you wanted to go ahead and deal with a COM name or an org name. So the system they built was segmented. You had these registrars, and they would be your interface to VeriSign or Affiliates or whatever registry you wanted to deal with. And here's what's fascinating. Let's say you have a decent registry, and let's say you have a really crappy registry. For example, some New Zealand registry had a really bad SQL injection bug, and Microsoft got hit, and a bunch of other big names got hit. You know what all of those big companies were able to do? They were able to take their name, remove it from the crappy registrar, and move it to someone decent. You can't do that in X509. You can't say, I don't want to be vulnerable to this crappy CA. I just want to have all my risk in this bucket. This is a system where you can move your risk to map to what you can actually do something about risk. You can manage it. You can deal with it. Now, it is possible to prevent yourself from being exposed to an untrusted certificate authority. It's just extraordinarily painful. You have to run a private certificate authority inside of your own enterprise. And lots of people go ahead and try to do this, and it's really expensive, and it's really difficult to maintain, and time after time, companies find out, oh wait, I have to deal with other companies. And how do I interact with other CAs? Now, there is a certificate authority system called the Federal Bridge CA. It allows various groups in the United States government to actually authenticate against one another. It's a miracle the damn thing works. This was not done at small expense. Everyone who built it deserves a medal for making it happen. For the rest of us, I'd like an authentication technology that does not deserve a medal if you get it to work. Look, interoperability not actually optional. The only people who think that large companies are individual groups that are all hive mind are people who have never actually worked at large companies. The reality is any large company is a collection of tiny little organizations that share a name and fight amongst themselves and hopefully don't let it get shown too much publicly. Everyone who clapped has totally been there. Cross-organizational authentication and operation is the rule. It is not the exception. This is your life. You have to be able to deal with people outside your org. You have to be able to identify them. You have to be able to work with them. You have to be able to get things done with them. Passwords work. If you have a string of text, that same string of text works with your org. That same string of text works with their org. That same string of text works with frickin' Yahoo. That is not something you can say with all of your smart cards unless you do things with extraordinary expense. That is a major reason why they've all been blowing up in your face. So, There's also the slight problem of delegation. X509 has a real problem. You would think with all of the complexities of being able to change certificates, of being able to say, I delegate this right to you, and this certificate leads to this certificate, and whatnot, you would think that it would actually be useful. You, my friends, would be wrong. The reason why X509 delegation is not useful is because a certain attribute was optional, something called name constraints. What name constraints let you do is the same thing that DNS lets you do. Say that you have control over a portion of the namespace. I cannot go to VeriSign and get a certificate for doxpera.com. I can't do it. I can't go to VeriSign, I can't go to Digicert, I can't go to Thought. I can get a certificate for an individual host at Doxpera. I can get a certificate for Wildcard, which would say, oh, all my devices will just have the same decryption key. That's a great idea. But I can't go ahead and actually become a participant in the X509 system because name constraints not actually reliably supported. This is a disaster. This means I need to go ahead and deal with an outside company every single time I add a node to my network. Every time I get a new box, okay, hey VeriSign, I got a new box. Hey VeriSign, I got a new box. And guess what happens? This is expensive. This is operationally inconvenient. This has potential information disclosure issues, and holy hell is a disaster for devices. Devices cannot be shipped with certificates built in. So what we end up with is self-signed certificates, which are also known as worthless. Now, DNS, by contrast, delegates very well. You have root, it delegates to COM. You have COM, it delegates to doxpera.com. You know how much I deal with the root and deal with VeriSign when I add a new host to my network? I don't deal with them at all. Let me tell you, all of my hosts are in DNS. Most of those hosts don't have SSL certificates. Think about that for a moment. That's probably the exact same way it is in all of your organizations. Cross-organizational dependency on some outside company dealing with your stuff leads to things not getting dealt with. Now, it is in fact possible to delegate with X509, but oh my God, it's painful. So this is what happens. What happens is some company spends some number of millions of dollars on a certificate authority system. They hire the guys, they build the systems, they pay whatever. They're all the way in, and all of a sudden now they realize time and time again, oh my God, we need to deal with other companies. How do we deal with this? How do we make this happen? We need to be able to issue certificates that not only are valid for us, but are valid inside of other organizations. So what ends up happening is this can't be done securely. If you get a certificate that allows you to sign other certificates, that certificate is going to be valid for any name. Anyone can go ahead. You can basically say, hey, I've got a certificate, it's an intermediate, it's a God cert, I can sign from bankofamerica.com. So you get to do this. The protection, the security is, I promise not to abuse my God level security. X509 security comes down to, I promise, are you shitting me? So there's at least two companies that if you have $5 million a year of income at your company and a little pile of money, they will simply hand you a God cert. There's no need for hacking, there's no need for begging, you just say, gimme, and they do. And that is the basis of a lot of delegation out there. It's not that the companies don't take security seriously, it's that a lot of their absolute best customers are like, hey, our shit's not working and we paid you a lot of money. What are you going to do about it? They say, here's the God cert. Go have fun. That's what happens. So, 2008 was not a good year for X509 certificate authorities. Mike Zussman went ahead and basically got a cert for live.com. Well, I said he had an internal server named www.live.com, and they're like, okay. I just gave it to him. What? I name my servers weird things. It's alive.com. I broke it. I mean, when you break DNS, you happen to break SSL as well, and pretty much break almost all the certificate authorities out there. This led to the fun stuff last year where I was getting phone calls from Finnish certificate authorities at like 6 in the morning. The BGP attacks by Avi Pilosov last year, he actually showed that any ISP could man in the middle pretty much any traffic on the internet if it so wanted and do so silently. Avi's attacks would actually allow it to see him to see those domain validation emails as well. So he was also in a position of being able to intercept SSL certificates. The big hack actually was at CCC last year, involved MD5. The MD5 algorithm has been known to be broken since approximately 1996. Don't worry, we're still using it everywhere. God damn it. The way this attack worked is you need to have a secure hashing algorithm. It kind of takes a fingerprint. So if you have some certificate, it says, "Hi, I'm Bob," or I guess in my case, "Hi, I'm Dan," that you need to have someone sign that. Sign that message that says, I'm Dan, and I Doc Sparrow research, and blah, 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 blah. First thing you do is you summarize it to a sort of fingerprint. This is what a hashing algorithm does. And then that fingerprint is what is signed. Well, to have a secure hash, it must be impossible for "Hi, I'm David," "Hi, I'm Jim," "Hi, I'm God" to have the same hash as "Hi, I'm Dan." And what happened is that the algorithm MD5 actually has what are known as collisions. You can actually have multiple messages hashed to the same fingerprint. So Stevens and Soderov did this really interesting work. What Stevens' contribution was he created what's called a chosen prefix attack. And in chosen prefix attacks, you can have two different messages. One that begins with "Hi, I'm Dan," and another begins with "Hi, I'm God," and then have a magic little blob put on after. And when it all goes to the hashing function, they collide down to the same signature or the same hash. And then a signature across that hash will apply to both "Hi, I'm Dan," "Hi, I'm God." And they actually implemented this. I mean, this was not theoretical. They went ahead, they found a certificate authority using MD5 that was predictable enough with its serial numbers, and they actually, at CCC last year, released or just demonstrated a certificate that was a illicitly acquired God-level cert. Now, there's a lot more where that comes from. A couple of us have been looking at x509, Moxie Marlin's Spike as well, and we've both come to pretty much identical conclusions, which is, my God, this stuff is fragile. Every time you turn around, every level of depth, there is ambiguity, and where there's ambiguity, there is exploitability. We'll start with the hashing functions. Yes, MD5 is supported and is insecure. You know what else is supported and is insecure? MD2. MD2 is actually a predecessor function to MD5. It's 2 generations back, and it turns out most things will actually support an MD2 certificate. Now you might say, "Oh, come on, Dan, this can't matter, right?" Look, yes, there was a certificate authority that was signing with MD5, but it's signing today. Like, it's actively using MD5 today. Well, I guess today being December of last year, but same difference. No one has been using MD2 actively since 2001. So how could this possibly be a problem? Well, I have kind of a theory. Anyone here familiar with the Final Destination series of movies? Crypto vulns are really weird in that they're ungodly slow. But we don't know when they'll burn us. We don't know how they'll burn us. We do know we're going to get burned. It's probably going to be epic. So this one begins with one of VeriSign's root certificates is actually signed with MD2. It has been there since 1996. I'm going to drink for them. All right. Look, how are we going to mess with this guy? So, what the fuck is with self-signatures? They have no reason to exist. You have effectively the cryptographic equivalent of "I am me, says I." Really? Best I can tell, and I swear to God this is the truth, the only reason I think we have self-signatures is because ASN1 libraries in the mid-90s really, really wanted to always see a signature there. So they put a signature there. No harm, no foul, right? Let's have some fun here. So you might ask, why MD2? Well, it was the 90s. It was the slowest algorithm, so it was considered the most secure. We didn't do security too well in the 90s. We don't do security too well now, but we really didn't do security too well in the 90s. There are many ways that a hash function can fail. A collision attack allows you to generate two things with the same hash. This is what Xiaoyun Wang actually demonstrated exploits of, starting from nothing, go ahead, make two things, give them the same signature. And I went ahead and my MD5 someday paper showed how to mess with that. Then last year, we saw the chosen prefix attack. This says, given two different things, I start off with them, fix them, make them collide. There's a third class of attack. This is called a preimage attack. This says, back in 1996, we created this MD2 hash. Could we create something else with that hash? In a preimage attack, you get to do that. Now, SHA-1 has nothing going on with preimages. Neither does MD5, neither does MD4, So, here's what you can do. Here's how you actually exploit the MD2 issue. That self-signature has no reason to be there, but ultimately it provides the RSA signature across that MD2 hash. If we could create something else with that MD2 hash, like, for example, a God-level intermediate certificate, we would generate that God-level intermediate certificate, we would give it the MD2 hash of the root, we would take the signature from the root, the self-signature that has no reason to be there, no purpose, we will give it a purpose. We will shift that signature down. It will validate, it will sign, it will work. Eventually. We do not actually have an MD2 preimage attack yet. In 2004, the attack I just described would operate with a complexity of 2 to the 104. Not going to happen. 2005, 2 to the 97. In 2008, we were down to 2 to the 73. Now, our largest known computational efforts have been at around 2 to the 63 complexity. I'd like to show you guys a bit of a graph. I think I know where this is going. So, we got two options. We can wait until we get completely owned, or perhaps, for the first time in cryptographic history, we can fix something before it blows up in our face. Would you believe it? They actually agreed. OpenSSL's like, screw MD2, we don't need that crap. It's out of OpenSSL. Firefox has it out of Firefox 3.5. It'll be killed in 3.0 shortly. Red Hat's already shipped the new NSS, their new crypto library. VeriSign is reissuing a new self-signed certificate, but now self-signed with SHA-1, because it really apparently does need to be self-signed with something. Opera's waiting on VeriSign. Apple, Microsoft are working on it. Google's working on it. GNU TLS realized years ago they didn't want anything to do with this crap and disabled it. Awesome. How awesome would it have been if we had done this in 1996 and killed MD5 then? So, when I say this is going to blow up in our face, I'm not actually kidding, right? Because this particular certificate, if you look in the Internet Explorer certificate store, that's client authentication. So SSL isn't just used to authenticate a server to a client. On very high security sites, it will authenticate a client to a server. This MD2 route will authenticate clients to very sensitive servers. So I bet you might think, well, no one would possibly have that enabled, like actually working. No. If you actually connect to an SSL server, it's very helpful. If it supports client authentication, it'll tell you. It'll even give you a nicely formatted list of routes that it'll accept. And if you actually go, you'll see by default Class 3 Public Primary Certificate Authority on any IIS install that is supporting client authentication. So the bad guy takes their God level cert and just says, yeah, I want to log in. I'll be this guy. Cool. So this actually was not a trait that we had with the MD5 root that Stevens and Soderov popped. So I do want to be a little bit fair. This wasn't just VeriSign's problem. Quite a few companies were signing with MD2 up until about 2000, 2001. Now, the fact that these things expired, 8 years ago, that doesn't matter, because if you can spoof the hash, you can actually change the expiration date. It's very nice like that. But it does matter that most of these MD2 certificates are off the internet today. I did find a couple. Not actually true, there's one. There's a couple. I think nobody in this room is going to understand why this is hilarious. But if you do understand why this is hilarious, come up and grab a swig. Anyone understand why Rubicon would be awesome? Rubicon was an American con. It ranks as the only hacker con in history where the entire attendance was let out with their hands on the back of their heads. And this was actually, one of the few MD2 certs around. So, did this need to be fixed immediately? What is it with a couple of people not patching it? Relax. I actually went over to Leuven in Belgium, talked to Bart Pernille. He's Len Sassman's advisor, Len being one of the co-researchers on this. And the guy's like, wow, MD2 hacks would actually be useful? Oh, well, we probably won't see one in the next 6 months in terms of effective attacks. So it's bad, but you've got a couple months. So please do not crack the shit out of MD2 in the next 6 months. Thank you. Being said, it would be a totally offline attack. We wouldn't be able to tell. So what about existing CAs? I mean, the MD2 stuff hasn't been used in years, right? Is there any way to bypass present-day CA operations? Yeah, but first you got to drink. All right, so this talk came out of, anyone here know Meredith Patterson? This talk came out of her saying, I'm going to go home and see just what kind of crap I can put in a certificate. And I'm like, that is a terrifyingly good idea. There are two kinds of vulnerabilities, ultimately. There's vulnerabilities that cause the system to misuse memory. These would be your traditional exploits. And there's vulnerabilities that cause the system to see a different message than was intended. These are a softer form of vulnerability. These are semantic exploits. You've given a valid message, but it is read differently by different systems. Now, what I need you guys to understand for a moment is that certificate authorities and browsers talk to each other. Basically, a browser goes to www.foo.com, and it has no idea what public key it sees. So it says, effectively as mediated through certificates, hey, CA, is this actually the public key of www.foo.com? And the CA either says yes or no. This is all done with signatures and whatnot, but that's actually the communication that's happening. Now, how do you know that a certificate authority is actually saying something? If the certificate authority thinks it's sending one message and the browser sees that it's reading another, would that not be a vulnerability? And the answer is yes. And the fact that we're still seeing this crap, in 2009, comes back to the fact that we're just not very good at writing parsers. At the end of the day, language is hard. It has to be done a little more formally than we've been doing it. What I'm about to show you is a bunch of evidence of kind of half-assed parser design. At 11 a.m. tomorrow in one of the rooms, there will be a description of full-assed parser design. I don't know which room, but go find it. Len and Meredith are doing it. Do we know what room, actually?
Actually, I got an email this morning. They canceled. They couldn't come here. One was stuck in, the other was stuck in New York.
Never mind. Meredith is not actually going to be able to talk tomorrow. That sucks. Damn, because they actually had cool stuff and they were responsible for some of this work. But let's actually walk through the certificate authority pipeline here. The user generates a public and private key, submits what's called an x509 subject name with a public key in the certificate signing request. There's only one element in that that actually matters. And that is what's called the common name. So there's all this other crap based off of a system that was theorized would someday exist and never did. The only thing that is actually validated is the DNS name, www.foo.com, which goes in a field called common name. If the certificate authority approves of the common name in a certificate signing request, meaning it actually does the whole DNS thing and it validates that, yes, okay, I can trust this person, it has two options. It has the secure option of extracting the CN that it thinks it sees and generating that a certificate with that common name. Or it can say, well, I've got this big batch of crap. The only thing I care about and it looks good. Let's go ahead and allow that. That's the easy way to do it. That's actually the OpenSSL way of doing it. That is vulnerable to a bunch of attacks. So let's actually look at what OpenSSL does when it does the certificate authority signing. There are three ways that OpenSSL makes it easy to implement a certificate authority. The first way is you just go ahead and do the signing, and then you take this string here of the subject, and you see if you approve of it. Oh, there's cn.www.foo.com, is that okay? The second way is to dump the request and see if you approve of the contents of the dump. So you take this request that comes in, you dump it, you check the subject there. Or you can go ahead and dump the generated certificate and audit the subject. So you generate it, but instead of taking the output of the generation command, you dump the certificate and see if it's good before you send it to the user. Now, this should obviously bring to mind the idea of injection attacks. What if you have a string in there that says, oh, organization, my organization is badguyincorporated/cn equals www.badguy.com. And indeed, you get a straight-up injection in the output of all three of the tools. You'll get O equals badguy.com/cn equals www.badguy.com. Now, OpenSSL can defend itself from this. There's an option called nameopt. There's 4 different values you can put in there. All 4 of them are secure against this sort of injection. Not a single one of them is enabled by default. Damn. Now, is this exploitable? Well, it depends on the particular certificate authority, how they actually handle multiple common names. It turns out, however, interestingly enough, a genuine x509 subject name could contain multiple common names. You have an organization, a city, a state, a common name. What if you have another common name? What if you have 3? What if you have 4? What if you have 5? That's not actually defined, it turns out. And it turns out it totally depends. If you have OpenSSL, the first common name wins. If you have Crypto API as part of Internet Explorer, all common names. It's an all-inclusive policy. And if you have NSS with Firefox, the last common name is the one that the browser actually validates. Now remember, the certificate authority is trying to communicate with the browser. The certificate authority doesn't know which browser it's talking to, and all the browsers will hear different things. So first, all-inclusive last, we actually have a fail policy. How great is that? So, now it's usually that OpenSSL screws this up and only provides you the first certificate. It is possible to use the API securely. However, if you actually look in the field, you will find clause and Open1X and wget and bacula. Everyone just uses this x509 name get text by nid call. And it always only returns the first common name. If you have a certificate authority that is using this API, it too is only going to see the first common name. So what do you do with this? Well, the first thing you do is you need to be aware of wildcard policy. If NSS inside of Firefox sees a common name of star, it just assumes, well, okay, it's a God-level cert. This can sign for everything. Internet Explorer is a little more paranoid. It basically says, if I see star in a cert as the top level and that's it, this CA probably got hacked. And it just like chickens out and refuses to do it. So what you do then is you create a PKCS10 request with 3 CNs. The first being the attacker.com CN, because that actually is going to be validated against the attacker. The second is going to be www.bank.com, because you can still specify individual hosts for Internet Explorer, because Internet Explorer is going to see all 3. And then you round it out with just a star. So against Firefox, you get to spoof all names whenever you want. Now, we get to have some more fun. Now we get into some wonky stuff. What is a common name? Like, what is it actually, how is it represented on the wire? ASN1, who here is familiar with ASN1? I am so sorry. This crap's got like 3 ways of representing a length and 13 string types. What is wrong with these people? So ASN1 was designed to be very fast to parse. It's actually very fast to crash under fuzzing. It's really, really hard to write a solid ASN1 parser. When the Protos guys actually fuzzed ASN1 in 2002, they pretty much broke every router on the planet. Now, it turns out that this ASN1 is a channel for SQL injection. And this is great. It turns out XKCD and little Bobby tables helped secure the internet. I swear to God, it went exactly like this. Little Bobby tables came out, it got passed around a bunch of geeks, and the certificate authority guys were like, holy crap, someone could put a drop statement in there. Actually happened, according to Peter Gutman. In ASN1, common name is not addressed with the characters COMMON space NAME. I mean, that has like language translation issues. So what they do is they put everything into kind of a numeric namespace. So instead of 2543, instead of common name, you say 2.5.4.3. And that would be what's called an OID, an object identifier. 2543 is the only object identifier that is actually cared about between the certificate authority and the browser. Everything else is ignored. But how is 2543 actually put on the wire? I'll tell you, it's not 2 period, 5 period, 4 period, 3 period either. No, that would be too easy. What actually happens is ASN1 basic encoding rules, BER, is a tag length value format, meaning you have a tag, some value that describes a type, 6 being the type of a OID, and then a length, which can be encoded one of 3 ways, and you really don't want to know them, and then a value, which is a certain number of bytes of whatever the length was. Now, in the values of OIDs, you have, it's what's called base 128, which means a number can be encoded one of 2 ways. You could either have, say, a 6, which is just, this is a .6, or it could be 86, which says, this is the number 6, and there's another number coming. It's like place value. You know, you have the 1s, the 10s, the 100s, only it's the same for like the 128s, the 128 times the 128s, the 128 times, you know, so on. Base 128 representation. So in the really simple mode, this is what a simple OID looks like. You have a 4 and a 3 for .4.3. For a slightly more complicated representation, we have, look at that right there, 86 times 4. We have an OID of 1.2.840.113.549.1.1.1. No, I don't know why they made it so complicated either. But what I want you to look at is the 8648. What that says is, take 6 times 128, so 86 minus 80 is 6, so 6 times 128, plus 72. 72 is the decimal representation of the 48. That's 6 times 128 plus 72 is 840, and there's the 840 at the top of the OID. Kind of making sense. You have like the capability for various numbers to chain in a row. So this is interesting. First off, you can have leading zeros. So instead of 2543, you can do the hexadecimal equivalent of 25403. Because 80, that's 0 times 128, which is 0, plus 3. So you actually can have an arbitrary number of 80s before the 3 in 2543. What happens? Well, OpenSSL is not fooled at all. Its actual OID resolver says, well, I see 2543, but that's not a common name. And indeed, it is the same with Netscape, which also sees 2543, but does not see it as a common name. Internet Explorer, common name. You can actually have a certificate with 25403, and it will resolve it back to common name. Semantic integer overflows. These are fun. You can actually, and this is kind of neat, integer overflows are one of the most common bugs in software today. I have not actually met a non-security developer who has actually realized that numbers wrap if you multiply them too large. They don't wrap in, human space, but if you have a 64-bit range and you say 2 to the 64, that's also 0. The number's too big to fit in the space. It wraps. Now, if you're saying this is usually used to exploit memory allocation, you say, hey, I want you to allocate some huge number of items. That wraps to 0, and now you can go ahead and the system thinks it's allocated a huge number, but it's actually not, and you get to write unallocated space. It turns out this can work semantically. What if you have 2, 5, 4, 2 to the 64 plus 3? That's what it looks like in hex. You have the 82 and a bunch of 80s. It turns out OpenSSL does not care because OpenSSL has what's called a big num library. And it actually expands out 2 to the 64 all the way. It is not tricked whatsoever. Firefox is totally kind of tricked. It sees it as 2543, but its OID resolver sees nothing wrong with it. Sees something wrong. This is not the byte sequence that I was looking for. And it actually has it as 2543, but does not see it as CN. Internet Explorer sees it as a CN. Awesome. So, that being said, most CAs are going to extract the common name and throw away the rest. Is there anything malicious that we could get into the common name itself? Something that could get in there, that has to be in there, has to be seen, but you can't throw it out. Well, let's actually look at what is in the value of a common name. You have an object identifier, 2543, and you have a printable string, www.docsparrow.com. Type 13, length 15, and there's the actual ASCII for www.docsparrow.com. There's some magic that we can do in that printable string field. First off, there are 13 different types of strings in ASN1 because they hate me. And the easy thing you can do is use some of the multi-byte encodings. It turns out this creates a trivial read AV in OpenSSL PKCS10 parser. So what they were doing is they were saying, wait, let's keep reading until we're at the end of this string. And then they would skip either 2 bytes or 4 bytes until they got to the end of the string, the exact value of the end of the string. If you gave it a string that was not at the actual offset, either 2 bytes or 4 bytes, say you gave it a 7-byte string, it would miss the terminator and jump right over it. This was very exciting. I was, oh, holy crap, I wasn't even trying to exploit this. I'm already getting a segfault. Sweet. Not exploitable. Why? Because OpenSSL does not actually write any memory after that overflow. It just keeps printing out some dynamically growing buffer and eventually hits a guard page and blows up in your face. But it blows up securely. So at best, it's a DOS. Props to those guys. They wrote some secure code. But there is something fun we can get in there. There are 2 ways of ending a string like www.docsparrow.com. One way is with an explicit length field. So ASN1 gives you a length field that says, for the love of God, the next 15 bytes are this string, deal with it. Or you can have a null terminator. This is what is known as a C string. If you put a null terminator, an OXOO, in the middle of a common name, OpenSSL will see, say, www.defcon.org. No, literally, it will turn into /x00 www.oxoo.com. Any certificate authority will see this as, oh, this name is part of oxoo.com. I'll go find out who owns oxoo.com, which happens to be me. But every browser sees that as www.defcon.org. The actual name validated stops at the null terminator. Shit. So I do want to be open with someone else who found this. Moxie Marlinspike and I actually went to the same conference within an hour of each other and unveiled this attack. We have it mostly, we're getting it killed. Firefox 3.5 already blocks the null terminator attack. Internet Explorer and others will be blocking it at some point. And we have as many certificate authorities as possible no longer allowing this. No, I can't tell you which certificate authority screwed up and gave me the null cert. Jeff Moss knows and Alex Soderov knows, so I promise you can go ahead and poke them, but it has been validated. So, I'm pretty worried about this bug. Lots of people have fixed it. Anyway, I've got a couple minutes. I'll talk about what I'm actually thinking we need to do. Do I think the certificate authorities are useless? I'm sure a lot of you don't like VeriSign. I disagree with you. VeriSign has an important service that they can provide. It's not just hosting COM. There is a really hard and lame problem that we would like to define away, but we can't. And it's, www.bank-of-america.com looks enough like Bank of America for your mom. So, I mean, what are you going to do? Like, there's all these things that are called semantic collisions. They look similar enough to a real brand that you really trust, that you really want to give your credentials to, that screw all these crazy ASN1 length field attacks. Just go ahead and throw a couple dashes in until you get a name that isn't actually already taken. This is a necessary consequence of having what is known as a open namespace. Anybody can put a name in DNS. This is what a necessary consequence of the fact that DNS is delegated. I will always be able to create www.bankofamerica.com.doxpera.com. That is my power. That is my ability. We need a way that I can't get a SSL certificate for that. And that can't be done with normal certificates, but it can be done with this new crazy thing called extended validation. Extended validation involves actual lawyers on the actual ground in the actual language that's being spoken, and they have awareness of the brands at play. This cannot be done with leet crazy technology. This has to be done with expensive people. Now, is extended validation perfect and the answer to all the threats in the world? No, no, no. Look, if you actually have a certificate for www.bankofamerica.com, extended validation does not stop you. It was never designed to stop you from messing with the real green bar experience, www.bankofamerica.com. The reason for this was very simple. The average website is composed of something like 10 different servers, from analytics to image servers to all sorts of crap. If you needed to go ahead and update the SSL certs with all of these things, with crazy expensive lawyers, no site could be defended by the green bar. So the browser developers said, you know what? That's not a problem we're trying to solve. All we're trying to solve is let's make it so bank-of-America doesn't work. But don't worry, the certificate authority marketers got a little bit ahead of the game and kind of said a little too much. So there were some attacks by Zussman and Soderov that just completely demonstrate that that barrier doesn't exist. So what do? The reason I told you about extended validation is so you can see how well this works out. DNSSEC, just for fixing DNS, is a little bit overkill. But DNSSEC, so your self-signed certificates actually have a reason to be trusted, so that that public key is validated not out of some crazy x509 contraption that doesn't work well, but instead works out of a smoothly excluding, delegating framework. That's awesome. You have your certificate, the certificate is validated via DNSSEC, and if you look at it, the certificate can have all the extensions and all the cool stuff and all the third-party validation that we get from VeriSign or from Thought or from whoever has boots on the ground. Extended validation could be made to work as it is supposed to, in a way that can exclude all other certificates, but this particular one that VeriSign has asserted is actually safe. That is what DNSSEC can allow. There's a lot of stuff that we're going to be able to fix once we're actually able to do things with DNS. We cannot fix it with x509 alone. So that's the deal. That's what I've been playing with. I'm open for questions.
Matt? Hello, hello, hello. Okay, well, I have a microphone. Questions? Isn't there another microphone? Oh, I'm sorry, camera.
No angry people running a CA who hate me for crapping on your parade?
Raise a hand. No? Oh, there is? There is? Was there a question? Oh, I got a question. All right. Come here.
Yeah, hello. I got one question regarding to the race to the bottom in quality that you mentioned. I remember doing my first SSL cert somewhere in the 90s.
I know where this is going.
And even back then, for a regular SSL cert, I had to go through all kinds of hoops and to provide business papers to the CA.
Yeah, you don't have to do that anymore,
And
do you?
you don't have to do that anymore. What is it to stop this with domain name services as well? You have to have some sort of.
Only one registrar can mess with your domain name at a time, versus every certificate authority can issue a certificate for you. If your domain name is with enom, Network Solutions cannot screw with you, no matter how broken their process is. That's awesome.
Okay, there's just one thing. We are paying the wrong people. Usually, the user would have to pay the CA to verify the bank, and it's the other way around. So this is, I think, the root of the problem.
I want to be able to pay someone a lot of money and have no one else be able to do that somebody's job. I want to be able to pay Mark Monitor and say, dude, you control my name, you control my keys, you make sure nothing bad happens, and I don't want some lend certificate shack to be able to mess with my certificate or mess with my domain name. This is a property of DNS. It can never be a property of x509.
Okay, we're pretty much out of time, but there was one more question on my side. Yeah, how many more questions? Well, we're pretty much out of time, so I'm just going to grab a question that's over here.
Very quick. Do you think that DNSSEC has any chance of being deployed, as it's been, I think, the 6th iteration of this protocol? It's been a complete contraption.
Hang on.
Yeah.
Let's get the damn root signed. Nothing matters until the root is signed. DNSSEC is a worthless pile of code until the root is signed because it can't solve any problems efficiently. DNS has worked amazingly for 25 years. Not perfectly, but better than most things. You tell me look, the DNS names root servers were there 15 years ago. They'll be there 15 years from now. What else in all of technology has a 30-year lifespan? Nothing. Absolutely nothing. Look, DNS has been there. It hasn't been perfect, but it's been okay. Trying to do DNSSEC without the root, without the foundation that makes DNS work, is worthless. If you want to have DNSSEC, you got to let DNS be DNS. You got to have a root. You got to have one root as opposed to the unlimited 500, 600 root disaster we have in x509 today. Give me the one root, and then we can see the development that will lead to things actually being secure. I think that's all we have time for question-wise, so I'll be outside. Come bug me. You guys have been great.
So just for anyone who wants to know, coming up in this very hall, identity processes with Winfried Tilanus, and that's all about privacy. Yes, laugh, I didn't rehearse saying that. And Stone Bootkit by Peter Kleisner at 10 o'clock. No, yes, 10 o'clock, right here. And bye-bye.